Assalamualaikum warahmatullahi wabarakatuh, and hi to my students. Welcome to another bonus video lecture. This time is regarding the proof for the case of function. And in function, you learn there exists three types of function. Specifically in this manner is one-to-one function, and also onto function, and bijective and also bijective, one-to-one and onto. And suppose you get this kind of statement: prove a given function that maps integer to integer, domain to codomain, integer to integer, such that fx equals to x plus 2. Very simple one. You can start to visualize whether this is a 1, 2 or not, like this. I have 1. 1 will be mapped to 1 plus 2, will be 3. 2 will be mapped to 2 plus 2, which is 4. 3 will be mapped to, okay, the function x plus 2, 3 plus 2 is 5. If you have this simple representation, you will have to hypothesize. You might hypothesize that this will be a one-to-one function. But if you look at the bonus video lecture regarding proof, the statements for all you cannot put in terms of example. You must be in the full general statement. But of course, there is no harm for you to at least try to get the rough idea. And to prove one-to-one function, you must back to the basic definition of one-to-one. And based on the definition of one-to-one, fx is one-to-one if and only if fx equals to fy implies that x equals to y. Okay. Let's try to prove this question first by using this definition. For this question, the proof starts now. Fx equals to x plus 2, and for fy is y plus 2. If fx equals to fy, it means that x plus 2 equals to y plus 2. Based on simple linear equation solution, you minus 2 at both sides, then x equals to y. Therefore, my conclusion is fx is one-to-one. Very simple, by using the definition. Another question right now. This is the question where it is one-to-one. There also another function which is might not be one-to-one. For example, like this. Let f map z to z such that fx is given as x squared, the quadratic function, x minus 2. Proof f is not one-to-one. Again, the basic rough idea, you can try to visualize, and it also can be a counter example. Because this is false, you can use counter example. If it is 2 to the power of 2, x squared minus 2, 4 minus 2 will be 2. For negative 2, which is also answerable to 2, because negative 2 to 4 minus 2 will be 2. This simple indication alone can be your actual proof, but the proof must be written nicely like this. Let fx, directly to f2, f2 equals to 2 to the power of 2 minus 2 equals to 2, and f negative 2 equals to negative 2 squared minus 2 is also 2. Right now we have the condition, which is if f2 equals to f negative 2, but 2 is not equal to negative 2. Fx equals to Fy should imply x equals to y, but for this instance, F2 equals to F negative 2, but 2 is not equal to negative 2. Hence, x is not equal to y. This counter example can be used as your actual proof. This F is not 1 to 1. A further proper example of proof is explained in the slide. But this is the know-how. Next, we proceed for the onto, or the definition is also can be known as surjective. And surjective means that, okay, I think I mentioned this in my proper lecture. I said that in onto, if Fx is onto, then all elements in codomain is assigned. This is in the layman term. The proper actual one, it means that the definition of onto, if Fx is onto, then it means that every y in the given codomain, there exists an element of domain which assigns to it. Okay. For this case, okay, this is a layman term. This is the proper definition, the second one. And let's use the same example. Prove that a given function fx equals to x plus 2 is onto or not. Okay, again you can start with the visualization, and this time it must involve that every possible integer 1, 2, 3 and so on. 1 will be assigned to what? If it is actually onto, then 1 must have exist some element in the domain that such that fx equals to 1. For this case, in order for you to find what is 1, you let x plus 2 equals to 1, then x will be negative 1. So negative 1 will be assigned to 1. If x plus 2 equals to 2, then x will be 0. 0 will be assigned to 2. And if x plus 2 equals to 3, then x equals to 1. These three examples give you some hypothesis that all elements from the codomain Z here will be assigned. This will give you the basic idea. But again, for all, you cannot prove like this. You should prove by a general statement, and the proof starts now. Let y be an element from the codomain integer such that fx equals to y. And as fx equals to y, x plus 2 equals to y, and x equals to y minus 2. It means that for y, which is an integer, there exists some x, which is y minus 2. As y is an integer, y minus 2 is also an integer, and x will be an integer. In short, there exists x from the domain integer for all possible y from the codomain. You can double check with this counter proof. Okay, if y is 1, then x is just 1 minus 2, and that x is an integer. If y equals to 2, the x is 2 minus 2 here, which is 0, and 0 is an integer. It means for every possible elements in the codomain, there exists an element x which is an integer. As my conclusion here is that f is onto. You can look at the further proof on in the actual slide. We do one more example. This time is not onto. Let f be a function assigned from z to z. Fx equals to x squared minus 2. Proof f is not onto, and if it's not, then you can use counter example again. The proof starts now. I just think like this. Suppose I take element in the codomain, let's say 2. Is there exists some element of x here which can be assigned to it? The question, this is a question mark there. Based on this idea, I just let my fx equals to 2, and this 2 x squared minus 2 is equivalent to 2. For this case, x squared becomes 4, and yes, there exists the 2 in this case, which is 2 or negative 2. So this is not a good counter example. It means here, for this 2, there will be an element which assigned to it, which is 2. However, for the case of onto, it must be for every. Let me ask for the 3. For the case of fx equals to 3, x squared minus 2 equals to 3, and this x squared equals to 5, and x equals to plus minus square root of 5, and right now this is not an integer. And if it's not an integer, it means if fx equals to y and y equals to 3, there does not exist some x from the domain such that fx equals to 3. So 3 will not be assigned to any element of x here. If we want to prove a counter example, you must choose a suitable one. If you choose fx equal to, it does not show that this statement is not onto. However, if you pick fx equals to 3, it was find out that x will be the square root or plus minus square root of 5, which happens to be not integer. Therefore, this f is not onto. Okay, this concludes the proving for one-to-one and onto. And if you have further question on this one, you can ask me or Madam Anis. For the relation, I already covered the proving of relation. The relation also have many provings there, and it's also have been covered in the video lecture entitled relation. So I think that's all for the extra video lecture for bonus 1 for the proving of function. Till we meet again in another time. Thank you and goodbye.